In this section, we are going to learn our last test for determining if a series is convergent or divergent. And this test only will apply to very specific types of series, and those are our alternating series. An alternating series is a series whose terms consistently switch back and forth between positive and negative. And there is one little piece inside of the expression that we'll see that we'll be able to identify pretty easily to tell that we're dealing with an alternating series. So we will typically see this -1 to the n power as the n values alternate between even and odd. This -1 to the n factor will cause our terms here to switch back and forth between positive and negative. You might also see -1 to the n plus 1. The only difference that's going to make is whether the first term starts off as positive or negative, but it will still alternate back and forth between positive and negative. So we can easily identify these alternating series just by looking for this piece right here. Now there are some others that alternate that don't have that piece. They usually will have like sine of pi or pi over 2 or cosine of pi or pi over 2. So like naturally cosine of different multiples of pi will switch back and forth between positive and -1 as well. So once we recognize that we're working with an alternating series, there's a specific test that we can apply, and it is appropriately called the alternating series test. So an alternating series we very often only use that -1 to the n or n plus 1 to identify the series as an alternating series. But once it's identified, we really don't use it anymore. From thereafter, in our test, we only use the non-alternating portion of the series. It's convergent if it meets these two specifications. And it has to meet both. A sub n plus 1 is less than or equal to a sub n. What this means is that the terms are decreasing. And earlier in this chapter, we looked at how to determine if terms are decreasing, and we can do that definitively if we calculate the derivative for an and it comes out negative. But remember, we're only plugging in usually n equals 1 to infinity, sometimes n equals 0 to infinity. So for positive values of n only, that derivative will always be negative, which indicates that the terms are decreasing. The second requirement is that the limit as n approaches infinity of a sub n is 0. So we're going to look at a couple of these alternating series and try to tell if they are convergent or divergent. The first one we're going to look at is the sum from 1 to infinity of negative 1 to the n over 2n. So the very first thing we should recognize is the negative 1 to the n power is going to cause these terms to flip-flop back and forth between positive and negative. And if you want to, you could even write out a few values of these terms. When you plug in n equals 1, you're going to get negative 1/2. When you plug in n equals 2, you're going to get positive 1/4. If you plug in n equals 3, you get negative 1/6. Next, positive 1/8, and on and on and on. As you raise negative 1 to even and odd powers, the final result will switch back and forth between positive and negative, and then our denominator is just multiples of 2. So we only use the negative 1 to the n to establish the fact that this is an alternating series. After that, we're only using the non-alternating portion in the tests. So we've got 1 over 2 to the n. So first, to show that these terms are decreasing, we need to be able to take the derivative. So to take the derivative of something like this, we really would write it as 1/2 times n to the negative 1 so that we can do the power rule on it. So an prime is going to be negative 1/2 n to the negative 2, or negative 1 over 2n squared. This is always going to be a negative number, because no matter what you plug in for n, once you square it, it's going to be positive. Multiply by 2 and it's going to be positive. If you calculate 1 divided by that number, it's always going to be positive. But then there's always a negative symbol out front. So 1 over 2n squared is always positive, but then we're always negating it. So it is decreasing. The terms in this series are always decreasing. The next thing we need to confirm is that the limit as n approaches infinity of 1 over 2 to the n is 0. And we can use our little power rule here. The degree in our numerator is 0. The degree in our denominator is 1. And anytime the degree in the denominator is larger, that limit is in fact 0. That means that this alternating series is convergent. Another one really quickly, the sum from n equals 0 to infinity of negative 1 to the n plus 1 times 4 to the n all over 3 to the n. So we recognize this alternating piece in there. That tells us it's an alternating series, and we're going to prove convergence or divergence using the alternating series test. So the a sub n we're actually working with here is 4 to the n over 3 to the n, which we could also write as 4/3 to the n. So the first step is to show that those terms are decreasing. So if our a sub n is 4/3 to the n, the derivative, this is an exponential function. Anytime you have a variable in the exponent, it's considered an exponential function. So the derivative for this, the derivative for an exponential is always itself times natural log of the base. It does not seem like this value is guaranteed to be negative, the a prime. Natural log of 4/3 is a positive number. 4/3 to the n power is a positive number. It looks like this derivative is always going to be 0. that should be enough for us to just stop and say, no, this is going to be divergent, because we do not have decreasing terms. If you want to, though, you can be absolutely certain and calculate your limit. So we've got 4/3 to the n power, and anytime you raise a number that's greater than 1 to a larger and larger and larger power, that value is going to go off to infinity. So this is not 0. The terms are increasing. The limit is not 0. This alternating series is divergent. Because of the way that an alternating series works, it is possible to estimate a range for the actual sum. We haven't done sums of series, figuring out the actual sum for these series, since we talked about the sequence of partial sums and then the formula for the sum of a geometric series. Most of the rest of these series we were only concerned with finding convergence or divergence. But it is possible to estimate a nice tight little range of values that we know the sum falls within. And this is done using the remainder of an infinite series, or an alternating series. So before I just give you the definition for this, I want to show you an example. If we've got the sum from 1 to infinity of -1 to the n over n, I'm going to write out a few of these terms, and then we're going to write out some of the partial sums to kind of see what's happening. When n is 1, the value here is -1. When n is 2, the value is a positive half. When n is 3, it's a negative third. When 4, it's a positive fourth. 5, it's a negative fifth. All of the terms that have an odd n value are negative, and all the terms that have an even n value are positive. And this would continue on forever. So if we look at our sequence of partial sums, s sub 1 is -1. S sub 2 means add the first two terms together. So -1 plus a half is a negative half. S sub 3 means add the first three terms together. I already know that the first two make a negative half, and now I want to include my -1/3. So that would be -5/6. S sub 4 tells us to take the previous sum and now include the fourth term. So this is -10/12 plus 3/12 is -7/12. And then S sub 5, since I have 5 of them written, we're going to include the fifth term in with that. And we get -47/60, which is just a little bit more than -3/4. Well, technically, since it's negative, I guess it's a little bit less than -3/4. Now look what happens when we track the progression of this sum. All of these values are between -1 and 0. So S sub 1 is -1. S sub 2 is a negative half, which is right here. So we're jumping from S sub 1 to S sub 2 when we include one additional term in our sequence of partial sums. S sub 3 is -5/6, which jumps back very close to -1. S sub 4 was -7/12, which is just a little bit smaller than a negative half. -6/12 would be a half, and we've got -7/12. So when I include the next term, I'm at about here, S sub 4. -47/60, we said that that was just slightly smaller than -3/4. So that's our S sub 5. So you see this little window we're working in just gets more and more narrow. So the pattern that we're seeing, if I were to calculate S sub 6, I would expect it to be close to S sub 4, but in between S sub 4 and S sub 5. The farther we go, the more and more we're able to narrow down this interval here that we're certain the actual sum is actually in, if we were to do every single term out to infinity. So when we estimate the sum of an infinite series, we have to specify how many terms we're going to use. So the definition says if we let the sum of -1 to the n times a sub n be a convergent alternating series, remember it only has a sum if it converges, notice that every single time I did my next partial sum, it was always closer than the previous one. The sum is always within the next neglected term from the specified partial sum. So in words, sometimes this sounds really confusing, but this means if I were able to find the actual sum of my infinite series and I subtract off a specific partial sum, I know I'm within a sub n plus 1, because a sub n plus 1, if I were to include it in my partial sum, I know based on this pattern here that it will be within those blue parentheses, which is the interval that took me between my last two previous partial sums. Which means, and we're not guaranteed that the S sub n is larger or smaller, but we know a sub n plus 1 is going to be positive, so we do absolute values here because we don't care if we're over or we're under. But what this actually means is that the partial sum is somewhere on the interval. If we add that S sub n over, and the absolute values mean we need to consider a positive or negative a sub n plus 1 value. Our lower bound will be a sub n plus 1, where we subtract it, and the upper bound is going to be, let me actually say, this symbol right here means it's an element of this set. The farthest away we could possibly go would be our partial sum plus the next term. I'm always guaranteed that my sum, my actual sum for my infinite series, is somewhere in that interval. So we are going to use a fifth partial sum to estimate an interval for the sum from 1 to infinity of -1 to the n plus 1 over n factorial. This is an alternating series because we see the -1 to the n plus 1 term, and it is convergent, even though I'm not going to go through the test right now. Having n factorial in the bottom, those terms will decrease and go to 0. So they do meet our rules for being a convergent alternating series. We want to use a fifth partial sum. So I want to find S sub 5 And then the farthest away I could possibly be from the actual answer is just my next neglected term, the next term I would have used, which is a sub 6. So partial sum represents a bunch of terms being added together. A sub 6 only represents a single term in that sum. So to find S sub 5, we need to add together the first 5 terms of that sequence. So we want to add together when n equals 1, 2, 3, 4, and 5. Well, when n is 1, we're going to have positive 1. When n is 2, I'm going to have minus 1/2. When n is 3, I'm going to have positive 3 factorial is 6, so positive 1/6. When n is 4, I'm going to have negative 1/24. And when n is 5, I'm going to have positive 1 over 120. This is S sub 5. We are adding together the first 5 terms of the sequence, and we want to get, I'm going to get both a fraction and a decimal for this, this partial sum. So we get 19/30ths, which is approximately 0.6333. Now, what we've done is we've bounced back and forth within some little range, and since all of my terms are decreasing, that range is getting more and more narrow as we go. So the farthest I am allowed to jump away from S sub 5 is just what the A sub 6 value is, because I'm guaranteed that the A sub 7 value is going to be the opposite sign and smaller. So A sub 6 is what we would get if we plugged 6 in there, and I get negative 1 over 720, which is approximately negative 0.0014. So just by using 5 terms, we are able to create an interval. I know that the actual sum for the infinite series is somewhere within the interval S sub 5 minus my A sub 6 and S sub 5 plus my A sub 6. Now the sign on here we don't really care about because I want to make sure that the value on my left is the smaller one and the value on my right is the bigger one. And we can do this with fractions or decimals. So in fraction terms, when I combine my 19 over 30 and subtract off 1 over 720, because that's as low as I could possibly go, in fraction form I get 91 over 144. In decimal form I get 0.6319. And then the farthest we'll be away on the right is if we were to add them. In fraction form, that's 457 over 720. But in decimal form, and the decimal form is a lot more useful because you can actually see how tiny this interval is going to be. It's 0.6347 approximately. So sometimes we need this one because we're asked for an exact values, but sometimes the decimals are easier to understand and actually see. If you look at the difference between those numbers, they are about 28 thousandths. So we're able to estimate our sum to about it would be 28 10,000ths. We're able to estimate it to about 3 thousandths. So that's amazing with only using 5 terms. Now every single sequence or every single series is going to be different. It just so happens that the factorial makes these terms get small really, really quickly. So that's how I'm able to find a very, very narrow window to use for my interval. If the terms didn't get small quite as quick, like if this was a 2 times n in the bottom, and our terms very slowly went to 0, then we'd probably have a much bigger interval here to work with to estimate our partial sum, to estimate our sum. But we're actually able to find within about 0.03 where our actual sum for our infinite series is, using a partial sum and then adding or subtracting the next possible term that would have been included. The last thing we're going to talk about in this section is just a bit of terminology. And it's absolute and conditional convergence. With alternating series, we can classify our convergent series based on what the series would do if it were not alternating. So if, let's say, the sum of a sub n is a convergent alternating series, we could give an even more specific classification for this convergence if we check to see what would happen if our terms were not alternating. And the way that we do that is we put absolute value bars around it, and that just forces all of our terms to be positive. So we say that the series is absolutely convergent if the sum of our absolute values is convergent. So what we're checking here, if you notice the rule for the alternating series test, it's not very strict. All we have to do is have decreasing terms that are going to 0. There are other series that we've seen that have decreasing terms going to 0, and they were divergent. So the rules for alternating series are much more lenient. So if we can take the alternating part away and it's still convergent, then the alternating series is called absolutely convergent. That means it's not dependent upon the fact that it's alternating. However, we've got some series that if they were not alternating, we could not classify them as convergent. So again, we're working with a convergent alternating series, but we would call that series conditionally convergent if we take away the alternating, which means we're just looking at the series of the absolute values. And once we take away the fact that those terms are alternating, our series now becomes divergent. What this means is that our series was only convergent because it was alternating. So there was technically a condition on the convergence. And I'm going to show you 2 quick examples of these to finish up this section. Both of these will be convergent because we want to just prove absolute or conditional convergence. But we can check really quick to make sure they're convergent, get a little bit more practice with our alternating series test. But really our ultimate goal here is to say whether it's absolute or conditional convergence. So the first one is the sum from 1 to infinity of negative 1 to the n over 2 to the n. You can check if you want to, because it's an alternating series. All we use this for is just to identify the fact that it's alternating. After that, we only use the positive portion that actually gives our terms values, which is 1 over 2 to the n. There are two things we need to do to show that this is convergent. We need to make sure that the terms are decreasing. Decreasing means that our derivative is negative. So in order to take this derivative, we should really pull that 2 to the n into our numerator as a 2 to the negative n. It'll be much easier to take our derivative then. This is an exponential function. So an exponential function always contains itself, and then we have to multiply by the derivative of the exponent, which is negative 1. And because it's not base e, we also need to multiply by natural log of the base. And if we clean this up a little bit, we have negative natural log of 2 over 2 to the n. Well, natural log of 2 is a positive number. 2 to the n, remember our n is only going from 1 to infinity, that's always going to be a positive number. And then we always tack on a negative, which is always going to change the value to a negative. So this being less than 0 proves that it is a decreasing sequence of numbers that we're working with. The second thing we had to confirm is that the limit as n approaches infinity for 1 over 2 to the n is going to be 0. Well, our numerator is going to be fixed at 1. But our denominator, as our n values get larger and larger and larger, we're going to be raising 2 to a larger and larger power. So our denominator is constantly increasing here, which makes the overall value of that fraction constantly decrease. So it is going to 0. So this just proves that it is a convergent alternating series. But we want to know, is it absolutely convergent or is it conditionally convergent? So what we do is we take the series that we were given and we put some big absolute value bars around it. And what that essentially does is it just cancels off the alternating part. And we're left with the sum from 1 to infinity of 1 over 2 to the n. Now this is different than what we did in proving that the initial alternating series was convergent. We were just kind of thinking of that as a sequence. We didn't have it inside of our sigma. But now we want to consider this new series completely on its own. So that is going to be a geometric series. If we rewrite it as the sum from 1 to infinity of 1/2 to the n, we see it's geometric. It's got an r value of 1/2. And remember, anytime that r value is between 0 and 1, that means it's going to be convergent. So this particular alternating series doesn't require the alternating part to be convergent. It would be convergent no matter what. So that's what we call absolutely convergent. The second one, I'm not going to go through all of the steps of proving that the initial alternating series is convergent. We're just going to kind of accept that fact. We've got the sum from 1 to infinity of negative 1 to the n plus 1 over 2n minus 1. If we were to check, we would see that for a sub n equals 1 over 2n minus 1, those terms are decreasing and going to 0. So it is a convergent alternating series. But to show whether it is absolutely convergent or conditionally convergent, we will look to see what would happen if we took the alternating piece away and just tried to calculate the sum from 1 to infinity of 1 over 2n minus 1. Now, there are a lot of ways that we could check to see if this is convergent or divergent. I'm going to do it with the integral test. So remember, the integral test says we could think of this as a function and integrate from 1 to infinity. And if this integral converges, then our series converges. If the integral diverges, then our series diverges. So this antiderivative, 1 over 2x minus 1, is 1/2 times the natural log of 2x minus 1. And we need to see what happens with that value if we take the limit as x approaches infinity. And then subtract what we get when we plug in 1. But if you plug in 1 here, you're just going to get 0, because we've got 2 times 1 is 2, minus 1. We end up with just a 1 inside of our natural log, and the natural log of 1 is 0. So we need to know what happens on this natural log graph as you plug in larger and larger and larger values of x. And even though the natural log graph looks like it kind of starts to level out, it really never does. This value, as x goes to infinity, does keep increasing larger and larger and larger, and we end up getting a y value that also goes to infinity. So this integral is divergent. And that means that this series is divergent, even though it came from a convergent alternating series. And what that tells us is that the only reason the original was convergent was because it was alternating. Once we take the alternating away, it is no longer convergent. So this alternating series is conditionally convergent. It is only convergent because it is alternating.